Hey, what's up everyone? Jason Turley here, more microcorruption, capture the flag. So continuing on, we're going through these microcorruption like embedded CTFs. And we haven't really had too much of a need to deal with like the actual hardware and peripherals. Maybe that will come in the later challenges, but so far we're getting our feet wet. These are like baby steps. We are learning about this assembly language and the calling convention and things like that. So let's continue on. Like it's taking very nice baby steps of like introducing very different security mitigations and things like that. So this lock, so the overview, we have fixed issues with passwords, which may be too long because if you remember in the last video, we're able to do a very simple buffer overflow and overwrite a variable on the stack that it was looking for. It was looking for a very specific value at an address to equal something, equal hex E8, just some arbitrary value. And we were able to write past the length of our buffer and overwrite this stack variable. So very, very simple buffer overflow. In this level, we'll be able to take buffer overflows a little bit farther and do something that we've seen 100 times on this channel of being able to overwrite the return address using something called return-oriented programming. Typically, you'd want to be able to execute shellcode, but for this level at least, we won't need to do anything like that. We won't need to actually run our own shellcode. We just need to return execution into a function that we can't access normally. So with all that talking out the way, let's actually look at the code, right? So coming over here, we have the disassembly pane. I like to scroll down all the way to the main function, and hey, it's one line of code. It's very simple. It's one instruction. All it does is call the login function. So if we come down here and we search for the login function, we can see the different things that this function implements. So enter your password. Remember, passwords are between 8 and 16 characters long. Before, it always prints out that message, but it doesn't enforce like any bounds check. So we see here this call to get string n, get sn. So get string or get n bytes of user input, right? So R15 is where we will be storing our user input, and we'll be writing this many bytes, hex 30 bytes. I think that's 64. Let's open up Radari2 or just RAX2. This is from last level. Let's click the screen. RAX2 OX30. 48. So that's 48 bytes of input that we have to play with. So that's way more than 16. So we will be able to write data onto the stack, but we don't know all that much yet. Like what do we want to overwrite the return address with, for example? So then it calls test password valid. If that's true, it will unlock the door and so on and so forth. So let's come over here to this test password is valid. It looks like it's doing some setup here. It's moving 0 into the -4 offset of whatever is in register R4. And then it's moving this value into R14. It's adding them together. And then it will call our interrupt with hex 7D. If we're not sure what that is, let's come to the manual and scroll down to hex 7D. Interface with the hardware security module 1. Set a flag in memory if the password passed is correct. And it takes 2 arguments. The first is the password. The second is location of the flagged overwrite if the password is correct. So these are the 2 arguments, R14 and R15. So I believe R14 will be that memory address, or maybe it'll be R15. Let's come through to the login function again, because I think those registers are used as well. Here, R15 is the stack pointer. So what is this saying? The first argument is the password to test. So this is where I'm a little confused on the calling convention. Is R14 the first argument, or is R15 the first one? So which one of these is the first argument? I'm not too sure with this calling convention. I'm so used to x86 and x64. Well, let's kind of just fuzz it, right? Let's come over here. I'm going to uncheck this input as hex. And let's just spam a bunch of A's. Let's just do Python 3 hex C print, or maybe A is overused. Let's do X. And let's just print out like 40. Let's grab this and let's use this for our user input and just kind of see what happens. I didn't set any kind of breakpoint. Let's just hit C to continue. The program is no longer running. Oh, we get something INSN, address unaligned. I'm not sure if that's like their version of a segmentation fault. Is there any like backtrack or backtrace command? Like in GDB, you can do like a backtrace to see what happened. Count number of CPU cycles. I don't really care about that. I don't see anything like that. Backtrace. But if we do look at our live memory dump, we see the stack pointer is highlighted, and then we see hex 58. It starts here, and then it keeps going. So this is our user input that I have highlighted here. So at least we know where we are writing our bytes. It looks like we caused some type of crash though. Let me come back here. Where are we entering this? Is it the login function? Let's set a breakpoint, I guess right here, right before we enter our user input. Sometimes it's useful to, when you're debugging, set a breakpoint, look at the layout of the stack before your user input, and then look at it after your user input and see what variables or values or registers that you have overwritten. So let's see, hit C to continue. We have to do reset. Continue. All right, so this is right before we enter our user data, and we kind of come here and we look at the stack, and there's a bunch of strings here and everything. Okay. Some of the stack memory is blocked off, like before. We don't have access to everything. Let's just hit C to continue. Let's slam in our X's. And I'm just gonna hit S to single step through. We're inside of our interrupts. Let's just get out of here. We're inside get string. It's restoring the stack pointer. Let's get out of here. And now here we are. So move the stack pointer to register R15. Or rather, set R15 equal to the stack pointer. So we see here, the stack pointer and R15 are both 43EE. So if we scroll down here, 43EE stores our user input. So we're writing directly to where the stack pointer is. If this is anything like x86 or x64, I don't see a base pointer or anything like that, but the return address should be nearby. We see the program counter. This is like the instruction pointer. This is the next instruction to execute. So let's just hit S. We're just going to be stepping through. I don't want to get inside this function, so let's type out. See if I can do next. I'm curious what will happen when we get down to, where are we at? Okay, sometimes this web console is a little bit buggy. That's not exactly what I had wanted to do. I'm going to set a breakpoint here. Essentially what I want to see is if we can overwrite the return address at all. I want to set a breakpoint right before we do any return out of this function, because we'd overwrite the return address of the login function, the stack frame or the base pointer and stuff like that. So that's what I'm curious to see. So let's reset. C to continue, slam this in, C to continue. We hit our breakpoint. So let's look at the contents of the stack. 43EE, we're going to add hex 10 or like 16 to it. So our stack pointer is here. And we're going to add 16 bytes to it, which should still land us inside of our user input, inside of these X's. So let's hit S to continue. Okay, so here's where the stack pointer is. It's nice and highlighted for us. And now we're at the return statement. So this should return here, right? To our user controlled input. Let's hit S to continue. And we see now, it might be difficult to see, but our register state, the program counter, is equal to 5858. That is our user controlled input. So this is where it's trying to return execution to. So we can hit S to continue. And I'm not sure what 2C 2D is. Read 2C 2D. It's like all blank. There's but we saw for a second it was trying to execute our user input. So we've essentially gained control of that return address. So we want it to go to a different function. So if we can find the address of that unlock function, we can just have it jump there to this unlock door. So where is that at? I think it's just this hex 4446. Let's find it here. Yeah, 4446. So we're not sure how many bytes it takes to get to this. I think it's 1, 2, 16, 17, 18. I think it's 18 bytes, right? So this is 2 bytes. This is 16. 2 plus 16 is 18. So I think it takes 18 bytes of junk, and then we can start overriding the return address. So let's see if we can test this out real quick. Let's print out 18 A's or 18 X's and then like 2 A's. Let's reset the CPU state, hit C to continue, slam in this, hit send. I think I still have my breakpoint set. I have no breakpoints. Let's set a breakpoint on the return address of login function. Hit C to continue. Okay, so let's type S. Okay, it's returning to 5.8 still. It's not trying to return to 4.1. So maybe my math is a little bit off, which wouldn't be the first time. So let's hit reset. Let's hit C to continue. Let's paste this in, but I'm gonna get rid of these 2 X's in the front. So our total payload length is 18 bytes. It's 16 A's plus, or 16 X's plus 2 A's. Let's hit send. C to continue. S. There we go. So now our return address, our program counter rather, is pointing to 4141, and it will try to execute code from there, and it will fail. So now we can come back here and let's change this to like 16 X's. And then we want the address of the unlock door. So what was that? It was like 4446. And we have to write these backwards because it's a little Indian. So let's C to continue. Find reset, C to continue. Paste in 16 X's. And then 4644 because it's a little Indian, so it's swapped. And make sure we check this to make sure our user input is encoded as hex. Continue. Type S to set forward one instruction. This isn't what we want. 443C. How do we get there? Let me refresh the page. Maybe I borked something up. 4644. If this does not work, I have one more idea. Let's hit send. I don't think I have any breakpoints set. I want to set a breakpoint at the return address here. C to continue. Step forward. Okay, so I want this to say 4446, but instead it's 443C. So I'm not sure what I'm missing up there. But instead of 44 and 46, we can actually do these in ASCII, right? D and F. So D and F. So let's do this, 16 bytes of that, plus D and F. And let's use this as our payload. Reset, continue. I didn't mean to set a breakpoint there. Continue. Uncheck this now and check the hex input. Slam this in. There we go. Now our program counter is pointing to 4644. So if I hit S to continue, we should see ourselves inside of that unlock function. No, address unaligned. Not sure what we're messing up here. Yeah, it's not liking our input, but we were able to overwrite the program counter with the correct read 4446. Do I have my bytes wrong? 4644. D. Oh, I have my bytes wrong. It's little endian. We just went over this in the last video. 4644 is F and D. So let's switch this around. F and D. Come here. That's so annoying. That's between the endianness and then computers start counting at 0. I think those are like the two things I hate the most about computers in like programming. I think that's just like so unintuitive. Sweet. Now our program is here. So I had my endianness swapped. So that's why. So this calls interrupt with a value of 74, which simply unlocks the door if the password is correct. So let's step through this and we get the you win message. Okay, I was kind of going crazy there. So let's solve and just slam this in. So that's why it was not working. We had the endianness flipped. So that's it for that video. Hopefully that was entertaining and interesting. Very, very simple return address overwrite. We see that a lot for return-oriented programming. If something like NX, non-executable, or data execution prevention is enabled, where you can't actually execute code on the stack, you can either write to it or execute it, but not both. So maybe that will come into play in later challenges. But for now, that's all I have for you today, guys. Hopefully this was enjoyable. Like, comment, and subscribe. And as always, take it easy, and I'll see you in the next video.